Hi, guys. Wow, welcome. Like Jamie said, I am Angela Wilson. I'm from Arup in the Los Angeles office. Thanks for coming to Stonington, or to FME and Resiliency, where we're talking about Stonington, Connecticut. So without further ado, let's get started. A little bit about Arup and myself. I am with the Digital Insight team in the Los Angeles office, and as a member of the Digital Insight team, we're responsible for a lot of things: data transformation, conversion, web mapping, static mapping, programming, a little bit of development, so we wear a lot of hats. I've been with Arup for almost a year now, and before that I was with the UN World Food Program as a member of their GIS team, so I definitely have a GIS background. For those who don't know, Arup is a group of consulting engineers and designers and technical specialists. I think we have about 15,000 employees globally now, a few of which are in this room. So we are definitely a large global company. Here's a few of our projects, most of which you probably recognize, like the Sydney Opera House and the Beijing Water Cube. So a little bit about the project. Our Boston office contacted us and said they needed help with a resiliency project in the town of Stonington, Connecticut. There's a few pictures of Stonington. It's a quaint little town on the southeast corner of Connecticut. And while Stonington wasn't directly hit by Hurricane Sandy, they definitely felt the impacts from that storm and from similar storms, and they are particularly at risk for climate change and coastal flooding. Hazard mitigation reports from the town show that almost 1,200 properties are at risk of flooding. So the town contacted Arup and said they needed help with resiliency consulting, and so what we did was we helped put together a climate change vulnerability assessment for the town to show which areas were most susceptible to future flooding. So the first step was to actually download all the data. Most of the data I got straight from this town of Stonington itself. I went through and downloaded any layers that I thought might be useful for my maps later on. Stuff like boundaries, transportation infrastructure, any critical assets, so police stations, fire stations, things like that. And then I organized it in an Excel sheet where I had the original file name, what I was going to rename it to later, the data source, the data acquired, and this was good, one, just for organization, and two, I brought it back in and used it as a joiner later in my FME model. So here is an overall picture of what the FME model looks like. I'll zoom in on different sections and go through it a little bit further. So here's section one. What I first did with all the layers was I threw them all into a file geodatabase, and then expose the attributes. So I expose the base name and the feature type, and then use the attribute splitter to split up the feature types, because some of them had a slash in there that the feature types needed to be split on. Then I added a timestamper just to have a record of when the data was converted. Then was a coordinate system extractor, which now looking back I realized was not needed, but at the time I didn't know that because I was brand new to FME, because the next step was to reproject all the data into the correct state plane coordinate system for Connecticut. And finally, I brought back in that Excel table that you just saw, and I used that as a joiner where I added a few fields like the date I downloaded it and where the data source was, and a new field for what each layer would get renamed to. So the next few transformers were an attribute manager where I just went through and I fixed all the attributes that I had just added with the joiner. So some got renamed, like I said, a few got added. And then there was a geometry validator. Because of Stonington's coastal geometry, a lot of the geometries were actually pretty poor, so polygons that weren't actually closed or lines that were too short to even be lines. And this was causing the FME model to fail over and over. So the workaround was to add a geometry validator and then go through and filter all these geometries to see whether they were points, lines, or polygons, things like that. And you can also see that below I added another reader. This was just a shapefile that had the project area, so that each of the layers would be clipped to the project area so that no layer would be gigantic later on. Following the spatial filter, all the layers had to go through a geometry filter to filter them into point, line, or polygon. The lines had to go through a few extra transformers to test that they actually were lines. So we calculated the length, and if they were lines, then they got written out into a file geodatabase for all the lines. If they failed, they went into a file geodatabase that had all of the points, and finally, any polygons went into a third file geodatabase that had all the polygon data. So the final result were 3 file geodatabases that had all my layers that had been successfully renamed, reprojected, they had all their new fields added. And as you can see, they are split up into the type of geometry they are, and they've been renamed depending on which category they fall under. So society for all the critical assets data, hydro for anything having to do with water, transport for transportation infrastructure data, things like that. And then finally, we use all of this data to create a series of static maps that went into the climate change vulnerability assessment for the town. So here's an example of what one of those looked like. Here are some of the critical assets that are at risk of flooding. So here you can see all the critical assets that are at risk of flooding in the year 2050 if there's a 100-year flood event, which means that there's a 1% chance of a storm occurring every year. Similarly, a 1,000-year storm event is a 0.1% chance of a flood or a storm occurring. And it's also worth noting that the flooding data came from a third party. It came from the Woods Hole Group, which is an environmental consulting agency in Massachusetts. So the flooding data was not part of my data conversion. Here's a similar map, just another example of the 100-year storm event in 2050, showing some of the transportation infrastructure that's at risk of flooding in 2050. And finally, we combined a lot of the data and used it to do a few zoomed-in maps on different parts of the town, just so that the town could have a more in-depth analysis on more densely populated areas. And I think we made about 20 or so of these maps in total, and they all went into a climate change vulnerability assessment for the town of Stonington. So hopefully they can be better prepared in the event that there's sea level rise or another hurricane or any type of flood event. If you have any questions, I'm here to answer them. No? Is anyone from Stonington? Been to Stonington? Heard of Stonington? No? One of the, yeah, there was a bit of a learning curve. One of the guys on my team who's in this room, Roland, raise your hand. He is a big FME fan, and he got us all started with FME. Mm-hmm. Mm-hmm. What was the reasoning behind separating out your geometry types into separate geodatabases? That was the only way that I could get the model to work with the funky geometry that came in with the way that all the islands were on the coast of Stonington. It was like my second month of FME, maybe, so, yeah. Any other questions? Cool, thanks everyone.